Right, good morning everybody. Welcome to day 2 of PASC. This morning we're going to kick off with our interdisciplinary dialogue session, and I'm very pleased to announce the presenter and the interviewer for this session. So the person who's going to be interviewed and present is Paola Cinnella, who's a professor of fluid mechanics at Sorbonne University. Her research focuses on computational fluid dynamics, numerical methods development, optimization, uncertainty quantification, and machine learning for developing turbulence models. She's also editor-in-chief of Computers and Fluids and associate editor of the International Journal of Heat and Fluid Flow. And she coordinates the machine learning for fluid dynamics group of TAC, and we also collaborate together on an EU project. So I'd like to invite Paola to come up on the stage. And also inviting to the stage, I think at the same time, Matej Praprotnik, who's going to be conducting the interview. Matej is head of the Laboratory of Molecular Modeling at the National Institute of Chemistry in Slovenia and professor of physics at the Faculty of Maths and Physics at the University of Ljubljana. His research focuses on computer simulation of soft and biological matter. He's a recipient of an ERC Advanced Grant in 2019 and project coordinator of Multi-X Scale, which we discussed this morning, is a Euro HPC Joint Undertaking Centre of Excellence. So without further ado, I will hand over, I think, to Paola, who's going to start with a talk, and then you guys will proceed with the interview and discussion.
Thank you, Peter, for the introduction. This is the laser. Okay, so I'm going to talk a little bit how we can leverage HPC and AI, recent AI methods, to improve the sustainability of aviation. And the motivation of my work is the urgency of sustainable aviation. You can see here a graph given by Eurocontrol. Eurocontrol is the European organism which supervises air traffic. And this shows the number of the millions of passengers expected across the years. So we are here somewhere. This big gap is the COVID crisis. But after the COVID crisis, you can see that the air traffic is still going up. And there are 3 scenarios, given uncertainties, with the best case scenario where we expect in 2050 plus 20% of air traffic in Europe, and a worst case scenario where we expect almost 80% more air traffic. At the same time, the European Commission, through ACARE, which is the Advisory Council for Aviation Research and Innovation, has targeted a zero net objective by 2050. So not only we need to reduce the emissions we are producing by keeping the air traffic constant, but we also need to fast the pace to compensate the fact that the air traffic is expected to increase. And these are the ambitious targets established as the so-called ACARE Flight Path 2050, where the goal is to reduce by 90% the reduction of NOx emissions. This is nitrogen composites. The compounds. You have 75% reduction in CO2 emissions per passenger per kilometer. And, well, you can imagine that moving to electric aircraft or to hydrogen-fueled aircraft could solve the problem. But the problem is that more than half of the emissions is due to long-haul flights. And with the present state of the art, and even with the progress that we might expect in the next 30 years, let's say, of 25 years, electric and hydrogen craft won't make it for long-haul flights. They will basically cover 2% by then of the air traffic. So they will not be enough, definitely, to hit the net zero goal by 2050. So that's why we need a step change in turbo engine design, among other things. Of course, this is not sufficient. We also need changing aircraft operation, airport operation, and so on. But I'm a fluid dynamicist, so I'm going to focus on turbo engine design, which is much related to fluids. Okay, and how can we do that? Basically, what we need to do is to radically change the design of aircraft. So not just doing small modification. This is what designers are doing right now. They modify a little bit an existing design, and for doing that, they can reuse models which we know are wrong, but we know also more or less how we can correct them. But if we want to move to completely breakthrough designs, this is the case of the RISE engine proposed by a consortium led by Safran and General Electric. So it's a new concept of open fan rotor, and also you need to modify the core with a very compact core, a turbine, and a combustion chamber moving the fan. And also you have to study the integration of the engine with the aircraft with different position, care about the noise produced by the engine, care about aeroelasticity, so interaction with structures to avoid that, if, for instance, if you break one of the blades, you impact the aircraft and so on. And all this requires detailed studies. So presently, the current design cycles are based on rough models and then on extensive, expensive, and slow and iterative wind tunnel testing. And this must be reduced, otherwise we will never make it by 2050. So how can we get faster and smarter tools? So that's where HPC can come to the rescue potentially. So the idea is to move from these rough engineered models to much more detailed model which solve most of the physics. And actually a success story which has been told, I think, yesterday is about simulating such a complex engine by using so-called high-fidelity fluid dynamics models, which consist in resolving all the relevant scales in the flow field. And the problem with fluid dynamics of engineering system is that you have a large range, a wide range of scales. For instance, this picture here is a zoom in of the flow around the tip of one of the blades, and you can see that you have a large vortex generated, but the vortex is also composed by very, very small structures. And if you want to solve all the relevant physics, you need to solve all that range of structures, which means extremely fine computational grids, which also implies using high-performance computer to run this in a reasonable amount of time. And even in this case, you are not resolving all the scales, because, for instance, in these simulations, they are not resolving the scales very close to the walls. There are cases where you do need to know what's going on close to the solid walls. This is an example of the trailing edge of a turbine blade. And you can see that in this case, if you want to know what's going on in the wake, which is fundamental to know about the losses, the performance of this turbine, you need to resolve what's going on close to the walls. And close to the walls, there's a region called the boundary layer. Well, the state of the boundary layer is heavily affected by the state of roughness of the blade. And here you have two computations made recently in my group where we simulated the whole thing by resolving the roughness. Here you can see the roughness distribution along the blade. And so we resolved each small roughness element. You can see the mesh here. We are meshing every tiny roughness element. And that changes a lot, because if you don't take into account the roughness, you get this. So you get very strong, intense vortices in the wake, which are also generating sound waves here. And all this disappears when you put the roughness, because you have a much thicker boundary layer and a much more mixed out wake, and that completely changes the loss, which means that you are completely changing the performance, the predicted performance. Another case where you need to resolve much more details is this. Here you have a blade placed in a test rig. So the test rig is simulated by, you have these two profiled walls, and you have a blade here in the middle. And you have some turbulence coming in here and impacting the blade. And this also affects the state of the boundary layer, because it can trigger transition from a laminar to a turbulent state. So in this case, what you need to resolve is turbulence across the domain. So this is the turbulence resolved in the simulation. And you also need to resolve these very tiny boundary layers, which you can see here in the enlargement. So this is a crazy number of scales that you need to resolve. And of course, you can't afford resolving them all over the domain. So what we did is that we simulated this post-stamp domain around the leading edge, and this is costing more than 2 billion points, the simulation, and 1 million of CPU hours. This simulation here is costing, it's 1.8 billion points, and also of the order of 1 million CPU hours, a bit less than 1 million. Okay. So the problem is that if we want to resolve everything, well, that's the case which called direct numerical simulation. We resolve all the scales. That's impossible for engineering systems, basically. Then you have some compromise solutions, a large eddy simulation, where you resolve most of the relevant scales. That's what we were doing in the previous slide. But it's also very costly. Or you solve all the relevant scales, but not close to the wall. That was the first picture, the picture with the full roller. And then you have engineering tools, which are called runs. These are only resolving the average behavior of the flow. Unfortunately, these models are inaccurate. So just to have an idea of the carbon impact, you can see here that, for instance, a DNS simulation of a very simple configuration, a flow across a channel, so it's just across between two flat plates, so the carbon footprint is equivalent to the carbon footprint of a flight between Beijing and New York and back, just to give an idea of the carbon footprint, not to speak about the computational cost. So massive HPC resources can allow hero simulations, but hero simulation cannot be used for design and have this high carbon footprint. On the other hand, you have lower fidelity models, which are introducing higher and higher levels of uncertainty in the simulation. They are attractive, but yes, they are highly uncertain. They are not reliable enough for the simulation we want to do. Okay, so what we would like to do in the best world possible would be to get high fidelity quality simulations at the cost of low fidelity or even less. Why do we want that? We want that because we want to optimize systems. This is the optimization of a nacelle around an aircraft engine. We want to quantify the uncertainties in the system. In this case, you can have uncertainties on the operating conditions, uncertainties about the geometry, and uncertainties about the model. So this means running repeated simulation to quantify those uncertainties. And you may also want to have real-time simulation to control in real time what's going on in your system. So for all these cases, it's not possible to use the high-fidelity simulations, unfortunately. And so actually, presently we are relying on low-fidelity models. So here come the promises of machine learning. How machine learning can help in bringing high-fidelity quality in low-cost simulations. So the idea is that we can use machine learning to accelerate simulation by replacing some costly parts of the system of the model with fast AI surrogates. We can also use machine learning to improve our physical understanding and modeling by improving the models by directly learning from data. And we can also use some types of machine learning, such as reinforcement learning, alongside reduced order modeling for active flow control, so better performance. So the question, however, is, well, machine learning depends very much on the data you give to it. If you give low-fidelity data, you get low-fidelity machine learning model, right? Garbage in, garbage out. So is it possible to train machine learning models with high-fidelity quality, knowing that we can afford only a few high-fidelity simulations? So what we are working on in this project with Peter, but also other projects around Europe, is to use HPC to generate large-scale high-fidelity simulation where we resolve everything or most of the relevant scales, and then to use machine learning to learn significant flow patterns, build fast surrogates, and inform control tools. And together, we can hope to have something which is fast enough, but at the same time accurate and adaptable to different systems. So we can do this in two ways. One way consists in just augment the existing low-fidelity models by learning from data a correction term. It's like giving a magic potion like Asterix, you know, and you use these high-fidelity data to just augment the capabilities of low-fidelity models, but by keeping the cost similar to the low-fidelity model. And, well, low-fidelity model means that you can use this strategy to improve your turbulence model, transition model, many other sub-models which may appear in your computational fluid dynamics code. And the another possibility consists in fusing a mixture of low-fidelity and high-fidelity data to build a machine learning emulator of your fluid model. So instead of running a simulation, you just train a machine learning model which reproduces the flow, the relevant quantities you need for your design, and then you just look for an optimal design using the machine learning emulator instead of running your costly computational model. And of course, you can combine both strategies because you can, augment the models, the low-fidelity models, and mix this augmented model with high-fidelity data to build an emulator. The difficulty here is the extreme cost imbalance between the high-fidelity model and the low-fidelity models, with the cost imbalance being of several orders of magnitude, 3, 4, 5 orders of magnitude. So this means that when you explore your parametric space, you can only afford very, very few high-fidelity simulation, which is a challenge for machine learning tools. So the bottlenecks to overcome to enable the use of machine learning to build these, high-fidelity surrogates is, well, the first one is how we select informative training data from costly simulation. Once again, we can afford only a few hero computations. So we have to strategically select the simulation which can best inform our machine learning models. For that, we can adopt what is called an active learning strategy. So basically, we have some criteria, generally it's probabilistic criteria, which are called an acquisition function. This acquisition function says, hey, I don't trust your low-fidelity model in this region of the design space. So please run a high-fidelity simulation. Once we have run the high-fidelity simulation, we get labels. And the labels can be used to retrain to enrich and retrain our machine learning tool. And then we can again apply our acquisition function to check if there are other regions of importance for our design where we don't trust the model. And in that case, we can again query the very costly high-fidelity model and retrain. And so we can parsimoniously introduce high-fidelity simulations in the emulator instead of just running from scratch plenty of high-fidelity simulation, which wouldn't be affordable, okay? So we are drop by drop instilling this high fidelity in the emulator. Another problem we have to solve before we can use machine learning is, well, generalization, because machine learning models are very good at interpolating the data they have seen, but they're very good at extrapolating. And the problem is that if we want to design, we have to predict all the flight envelope, so we cannot trust a model which is good only in a small region of the flight envelope. This is called, in machine learning, out-of-distribution generalization, and it's a real challenge. So there is plenty of work going on this. And finally, it's aviation. You need to certify your system, right? To certify your system, you have to know how much you can rely on your predictions. And for that, you have to quantify the uncertainty in the performance you are predicting. And well, uncertainty quantification in machine learning model is also an open challenge. And for instance, to do that, we can use what is called Bayesian machine learning. The idea here is that instead of using a model, machine learning model here represented by a neural network, but it can be anything else, it can be random forest, it can be whatever you want. Basically, instead of learning static parameter, fixed values of the parameter, you can try to learn probability distributions of your parameter, given the few data you have observed and given uncertainties in this data. And thanks to that, you have a machine learning model which not only gives a prediction, but also gives a probability distribution around your prediction, which can be used for robust design or for risk-based design, for instance. Okay, so what's the difficulty? So just two examples. An example, how can we use machine learning to augment models? I'm focusing, in our group, we are focusing on using high-fidelity simulation to augment turbulence models, which compensates the fact that in a computational fluid dynamics code, we are not solving all the scales in the flow. And so for that, we need to select data, and typically we have this kind of complex simulations. But if we only train with a few of these simulations a model, if the model is simple, we can learn the parameters of the model, but basically we will never capture all the diverse physics we have in the flow, because the model will be too simple and will basically provide a sort of weak compromise among different needs for capturing different physical processes going on simultaneously in the flow. This could be the wake, the boundary layer separation, the corner separation, and so on. If we take a too complex model, a big, deep neural network, in that case, since we don't have many data, the most likely is that we overfit the case we have seen, and we can't use the model for predicting something else. So what we can try to do is to train the model to capture better all the simple physical processing individually, and then try to put together all this information. How can we do that? So the idea is that we want a model, a single model, but a model which is flexible enough to capture different physical processes. So instead of trying to train a big model, big deep learning model on plenty of flows, which we don't have because they are too costly, what we can do is to train the model to learn the physics, to learn simpler physics. So this is consists in training simpler models, which we call expert models, which are specialized to capture given physical phenomena. And then alongside them, we train what is called a gating function, which basically is a sort of classifier, of soft classifier, which understands which physics is going on where in the flow and tries to apply the most suitable model at the right place. With this, it is possible to show that you get in general better generalizability than by just training a big model. And actually, we have done this with a category of machine learning models which are open box machine learning models. Basically, what we have is that we have a dictionary of plenty of functions, and we train an algorithm which picks the best mathematical term to fit our data. And we train the models, don't care about what's B delta. Well, this is the terms of our model. B delta and R is what we want to train to correct our low fidelity model. We train them for different physics. So flat plate physics, shear flow physics, separated flow physics. So these are the expert models. And then we train a gating function, and we apply them to a more complex flow where we have some flat plate flow, we have some separation, we have some shear flow. So we have a little bit of each of these physics. And if you look at the blended model we have trained, it actually it reduces the error. The blended model is the orange, with respect to the individual expert model, but also with respect to a standard baseline model, which is the green line. So these strategies seem not to be bad. Then we can also, as I was saying, use AI to train surrogates. In this case, we are not trying to augment our model. We want just to remove the simulation and replace it with an AI surrogate. So the problem is this. So this means that we want to do some design. We have some geometric variables here, D1, Dn. These are the geometric variables. And we want to predict some quantities of interest of use for our design. So for doing that, well, maybe we have plenty of design variables. What we can do is try to project everything on a reduced space. So first we apply some model reduction. This can be done using a machine learning tool called an encoder. And then, in the latent space, we also reduce the quantities of interest. Imagine that you want to predict the velocity field. You reduce it to a smaller set of variables on the other side. And we want to train this using a mixture of low-fidelity and high-fidelity data. So for that, we can use machine learning models, here again represented by neural networks, but can be something else. And what we want to do is to use plenty of low-fidelity data to train the model, and as few as possible high-fidelity high-fidelity data because they are very costly. And for that, we can use an active learning strategy, which allows to smartly select very few high-fidelity data for training. So we did that in one case, and I'm just showing a result to convince you that it's really worth doing the effort, because we wanted to optimize this blade. Here you're seeing only the nose of a turbine blade, okay? This is the baseline blade, and we wanted to optimize this. You can optimize this using low fidelity or high fidelity. If you do that using low fidelity, which you can afford, you get this optimized shape with a crooked nose. And if you look at the high fidelity prediction of this crooked nose, you can see that this is almost the worst possible design using the high fidelity model. So what we learn here is that if you use the low fidelity model, you are misguiding the design, okay? And so using the high AI approach, we can actually obtain a LES fidelity quality model with much reduced cost. So I'm almost finished. So using a mixture, a smart mixture of AI and machine learning, we can go towards a new design paradigm which can foster greener aviation. The impact, of course, of these methods goes far beyond aviation, because you can apply that to energy systems, you can apply to climate problems, you can apply to biofluids, you can apply to materials, whatever you want. So high fidelity, AI augmented model or emulators, and then use these fast AI emulators for design. Only just before closing, is sustainability sustainable? Because, well, this other graph is reproducing the electricity consumption of data centers across the years. And here you can see the percentage of consumption due to different things, to the infrastructure, the network, the storage, the servers, the conventional servers, so including those you are using for running your simulation, and AI specialized servers, the blue ones, okay? And you can see that the part of AI consumption is fastly increasing, and this is the scenarios. This is what we had in 2024, and this is the expected scenario in 2028. So the consumption due to AI centers is exploding. So we also need, in parallel to including AI, remember the high fidelity simulation had a high carbon footprint, but AI also has a high carbon footprint. So we must be careful about having also sustainable AI and frugal AI, and I believe that this is one of the subjects we have to tackle in the next year if we want to make it to a greener aviation. Thank you for your attention.
So maybe you join me here, yeah, Paola. So hi, Paola. Thank you for your nice presentation to dive into your research. Yesterday we had two really nice keynote lectures, and where we learned that basically now that we have these HPC very strong supercomputers, and on top of that there is also a need for method development and actually code development. And if we combine all these three, we can really now, with this power of supercomputers, solve pressing problems of society, like biomedicine or drug design, or actually the design that you showed for sustainable energy or so on. And we also had another lecture that basically the second keynote, so where Elisa Molinari showed this discovery in inverse design by HPC and AI. We saw that basically we have now this fusion of HPC, data, and AI that actually allows you now to really make the inverse design and discovery of new materials. Of course, this is done for the chemistry, and it's a different scale than yours, but the philosophy is the same. So basically, you reach to the same conclusions, and we are applying this methodology and procedures all over our disciplines. And basically, okay, so your is really now in a different time and length scales that material design, where basically what you are doing is you try to solve Schrödinger equation for many particle systems. And here instead, because you are much higher on length scales and time scales, you are solving Navier-Stokes equation.
Sure.
Yeah, and actually this should be like interdisciplinary dialogue. So I should position myself somewhere. So I am in sandwich between these two extremes.
Okay.
I am using a set of Schrödinger equation or Navier-Stokes Newton equation of motion because my research is devoted to MD and actually similar ideas again, multi-scale modeling where you basically you are moving through the length and time scale by using different models where you lump many atoms. You go start for atomistic, and then you go up with coarse graining, and actually reaching basically also the computational fluid dynamics scale, but on nanofluidics. And it's the same thing. So you are trading the accuracy versus efficiency. Yeah. And basically what my research is then devoted is how to basically flow interacts with biomatter. So my ERC is devoted to the actually ultrasound-guided target drug delivery, where you have ultrasound interacting with small gas vesicles, but they are on micron scale. Now the difference to your research is actually that I am living really in the low Reynolds number regime. So this is quite different. Either we are simulating equilibrium stuff or nice shear laminar flows, and there are no turbulence effects. Yeah. So this is just to clarify that I'm not an expert on turbulence. And this is really the interdisciplinary dialogue. So I can afford to start asking a very naive question for the moment. So yesterday we heard that the turbulence is one of the unsolved problems, the 7 unsolved problems. So what is all this fuss about? Why is it so difficult? So I think that you already partially answered during this question during your presentation, but nevertheless, let's start with basics. And turbulence is this really nice thing that combines statistic physics and fluid mechanics, so it's not a surprise that physicists and engineers are obsessing over it. So, but can you please explain us what is the turbulence all about?
Well, turbulence is fundamental in engineering because, as you said, engineering systems are a high Reynolds number. So this means that convective terms in the equation, the inertia forces are dominating over the viscous forces. And if you look at the shape, the mathematical shape of the convective forces, it's a nonlinear term in the partial differential equation governing the flow. So this nonlinearity leads to a chaotic system. And it's not yet proved that turbulence is the stable state after you perturb, a laminar flow. If you perturb a laminar flow, you introduce instabilities in the flow. Well, we kind of expect that at some point we arrive to turbulence, but it's not yet mathematically proved that turbulence is the stable state of this chaotic system. There are people working on edge states. The difficulty is that mathematically these equations are very difficult to handle. So what we are mentioning is that, Navier-Stokes equations, the proof of the existence unicity of solutions for the 3D Navier-Stokes equation is one of the millennium problems in mathematics, still open. And basically people have gave up about having mathematical solutions of these equations. They try to just understand the physics empirically by running simulation where they resolve most of the scale with the best accuracy possible. But of course, this empirical approach means that if you want to really to get the right dynamics, you need to resolve all the range of scales. And if you skip some scales, you just skip them, you get the wrong dynamics because you are missing part of the energy, mass transfer, momentum transfer, which is happening at the lower scale. So all the problem of turbulence is that you are trying to model what you are skipping in your simulation. So you don't have at all any analytical description. The system is chaotic. This means that small changes in the initial and boundary condition are leading to instantaneously completely different trajectories of your system. This also means that if you introduce small errors in a very short time horizon, the solutions are completely diverging. And still you need to you need some correct representation of the statistics of your system. So you are assuming that even if you have this perturbation, all systems, reasonably similar systems, are all converging to the same attractor. So they are characterized by the same statistics. And you want to get those statistics right, even if the detail of the scales is not right. And computationally, it is very challenging. It's challenging because you have several orders of magnitude of scales to be captured in the same simulation.
There is something similar in soft matter. It's called active turbulence. And it's actually a low Reynolds number. So
microswimmers.
Yeah, microswimmers and that. So yeah, it's similar stuff.
Yeah, the difference is that I think that in microswimmers, you have, actually the governing equations are linear. But the chaoticity comes by the fact that each swimmer can interact with the others, and so this collective motion generates a sort of turbulence, while in Navier-Stokes, it's really driven by a non-linearity in the equation. So, yeah.
Yeah, thank you. So, but from your presentation, I figured that experimental data, they are not enough, and the experiments, let's say, to model, to design this, are extremely costly and lengthy in time. So basically, this is not the way to go. We need HPC allows you then to do this kind of simulation. And he said that precisely because what this challenge is about the turbulence, that you need to do this direct numerical simulation. In principle, they are the only one that are really accurate enough. Are they accurate enough? So
that's a good question, because we assume they are accurate enough if we can perfectly describe the geometry and the boundary condition. But the finer scales you are capturing, the more detail you need to know about the boundary condition and the geometry. One example was the rough blade. At the beginning, we were just running the simulation. This is not DNS, this is LES, but we are resolving well most of the scales. But we neglected surface roughness, and we were getting a completely wrong behavior in the wake, and we compared with the experiment, we couldn't match the experiment. And so we were despaired, because how it is possible? This is the best possible simulation we can run for this case. And then we understood that the blade was rough. And so we introduced even more detail. So yeah, we're right. In principle, it could be very accurate, but you need to take into account really everything, because it is very sensitive to any detail you put in your computation.
And then, but of course, this is not feasible all the time, so you are introducing these simplified models to solve the same problems.
Only in the mean field, let's say.
Yes, the eddies, large eddies, and so on. But they are, to my surprise, so I understand that, if you want to really understand the turbulence, and you have to go into the core of it, you need to resolve all the length scales and all these movements. But I was assuming, because for the design of this engineering stuff, you could really get away with that. So you could, but then you show that you get really wrong results.
Yes.
So here you really need, also for the design, not only for understanding, you cannot really do approximations like you would assume that in engineering we usually do some sort of.
The problem is that when you use this low fidelity model, you basically skip all the turbulence scales. You only resolve the mean flow. But the turbulence scale are there, and they are transporting mass, momentum, and energy. So you are using a very rough model. Historically, we use relative gradient approximation to emulate this mass, momentum, and energy transfer, which is wrong, because, it's a linear model, and turbulence is nonlinear again. And those models can work well for some relatively simple flows, but if you go to even more extreme design, you have more complex physics going on, and you are going beyond the limits of these low-fidelity models. And so if we want to go to breakthrough designs, we can no longer trust our historical low-fidelity models. So either we need to augment them using AI, or to replace them by more costly high-fidelity simulations.
And this, as I said, this strategy to enrich the surrogate models with data from the so-called data-driven models, it's applied to many other disciplines as well. So in biomolecular simulation, we are using it. In material science, it's the same thing. So in biomolecular, we typically develop. Yesterday, we were saying that MD is the wrong model, but if you use the DFT-based force fields, I guess you get chemical accuracy, and this is the way how you actually nowadays we are doing this material simulation. So again, it's the same strategy as used here. You presented some strategies like for AI, how to actually enrich these models. But so this is the ideal situation. So I understand that, so especially in this complex systems, you have this interplay of length and time scales, and all this stuff works really if you would have a time and scale of separation somehow.
Yes.
And typically this is not the case. So what are the problems here in your research? So you show these large eddies, they are like coarse-grained models, coarse-grained objects.
Yeah.
But I mean, if you go to other situations, so other, let's say, typically when you train your model to a certain geometry or certain physical condition, then you move away. Is it still working or not? So
no, that is one of the points. That's what I was talking about, the out-of-distribution generalization of the models. I think that you just brute force train a machine learning model using the data you have. The model is not understanding the physics. It's just mimicking the data it has seen at training. So if you try to extrapolate to another flow, well, the model is probably very wrong because it's overfitting the data it has seen at training. So what we are trying to do is to teach the physics to the model. So because if you simplify the problem, so you have a very complex system, but in many cases you have regions when you can identify a dominant physical dynamics, right? So in those regions, you can train these expert models, which are very good at capturing that physics. They're probably bad at capturing a different physics. But if you combine this with some classifiers which tell you where, with some probability, you should be applying a model, then basically your model will generalize better because in a completely different context, it will recognize the physics, you know? If I have boundary layer physics here on a plane, let's say, and then on, I don't know, a helicopter, it recognizes that it's still a boundary layer. So the boundary layer is behaving more or less the same, no matter what the macroscopic configuration is. And that's the same for a vortex, that's the same for separation and so on. Of course, there are some phenomena which are still specific to the case, so probably you will need to retrain. But the advantage of using several competing models and mixing them is that you can also use the information from competing models to measure the uncertainty. So if the experts are very, spread out in predicting, you can say, okay, this region has a large uncertainty bar, so probably we cannot trust the model, and we can run new simulation for this specific physics and enrich the model. So you can, use, again, active learning to progressively improve your model.
So from your presentation, what you are describing now is basically how you resolve the flow.
Yeah.
So, but you were talking about the design. So,
sure.
And another way how to use AI is how to actually couple design into that. So, into this workflow.
Yeah. Well, the idea in design is that when you do design, basically you want to modify some design variables, for instance, the geometry, and know if the new geometry is improving the performance or not. And if you do that using HPC, it's just infeasible because one simulation is already a hero simulation, and you need several trials before you get an optimal design. So that's not feasible. You can do that using low-fidelity model, but in this case, you can misguide the design. So the idea is to have these multi-fidelity surrogates where you use plenty of low-fidelity simulation to explore the design space, and you correct the prediction with a few well-placed high-fidelity simulations. And then once you have your AI surrogate, you look for the optimum on the surrogate, which is a mathematical function, very quick to be queried, which you can couple with any optimization algorithm you want. If you trust it well enough, you can compute the gradients and do some gradient descent algorithm, but you need to really trust the gradients you get. Or you can use evolutionary algorithms like genetic algorithms. You can use simulated annealing. You can use, Bayesian optimization. That's what you are doing. We are using Bayesian optimization. And basically, this will tell you how you have to modify the design variables to move toward the optimum in terms of performance variable.
And in this sense, yesterday we heard that basically, I think that you showed this new machine, that the way how the machine engines are designed now, it's not the optimal way, so not the most efficient way, that basically different designs should be actually executed, but then the problem is that the whole thing would become too loud. So my question is, so how do you then deal? So this is the common problem also in the inverse design of materials. If you want to have several objectives and how to satisfy them at the same time. So how do you deal with that?
That's called multi-objective optimization. Actually, here, I'm a fluid dynamicist, so I'm mostly focusing on aerodynamic optimization. But in practice, if you want to do a new plane, you need multidisciplinary optimization. This means that you have to optimize at the same time the flow, the structure, the cost, the energy consumption, whatever. So in theory, you should run in parallel several models, each one predicting different things, how the structure is behaving, how the fluid is behaving, and so on. And then have an optimization algorithm which predicts the best compromise among these sometimes contrasting objectives. That's even more costly because you need a surrogate for the fluid part, a surrogate for the solid part, a surrogate for, And so for that, we are maybe at some point moving toward foundational models. That means, like large language models, like ChatGPT, so ChatGPT for sciences, where you train your model how to predict the fluid, the solid, and so on. But that's not for tomorrow, anyway. But it is something that people are looking at and trying to. For instance, there are people who are trying to develop foundational models which solve any kind of PDE. So you train a model to distinguish that if you have an advection term in the PDE, that gives this behavior to the solution. If you have a diffusion term, it behaves that way. If you have a reaction term, it behaves that way. And if you think about it, across many disciplines, you have problems governed by PDEs, which always contain this kind of terms. So if you could train a machine learning model to understand how to solve general PDEs, combining different behaviors, probably then you can apply the machine learning problem to any discipline. But we are not there yet at all.
But these are actually also, let's say, efforts in other disciplines, like in bio-community, like AlphaFold and all that stuff. And which we got, so there is two Nobel Prize were actually given to AI this year. So the question is then, the AI and all these neural networks is a long field, and actually HPC actually enabled this boost because before that they were just not useful. But now, we have new developments of AI, but they are mostly coming out of the big tech company like Transformers and Google and so on. So how do you see the role of academia in this context? I mean, because we were used to be like at the cutting edge of the development, and now we are not again, I guess. So are we just applying these different models that are developed by these big tech and to different fields and see how they apply? Because, for example, in biology, in AlphaFold, there is a different. So here you stress that you need the physics. In the biology, you throw out the physics and it works better because you have a very good data. And I don't know how it's the field here. So the data, the way how I understand you, are mostly done. They are
very difficult to obtain and they are scarce. This is a big difference, for instance, with a big success story in AI is weather prediction models, right? Because they have done the buzz because they said, okay, we now have these models like ForecastNet or Aurora or Pangus, these models, which basically predict the weather in the next few days 1,000 times more quickly than standard meteorology codes, and almost with the same accuracy. But those models are predicting a single system, which is planet Earth, using historical data accumulated since the 50s and also corrected with experimental observation, so doing data assimilation in the meanwhile. So this is a very special case. In most cases where you apply AI in fluid dynamics, you don't have all those data at all.
So you need to
and we'll never have them. It's impossible. So that's where you cannot use purely data-driven approaches. You need really to teach the physics to the model. And that's probably where academia and industry can some way, discuss together.
And is there also, so basically we saw that now AI drives the scientific research, no? But is it true also for the opposite way around? So that basically what we are doing in science would influence the development of AI?
Exactly, because you can't just take an existing AI approach, apply it to your scientific data. In general, it will not work. It would work correctly for the few data you have, and then you try. In physics, we want a model, or in chemistry. What we mean by a model is the inductive-deductive approach, right? You observe something, you deduce the physical behavior, and then you can predict an unseen case, right? And that proves that you have understood the physics. But with an AI model, a basic AI model, you haven't understood anything. So that's where we need to train the models to understand the physics, and we are modifying the AI approaches because we are going toward these physics-informed, physics-aware, context-aware AI models, which is a new discipline, very new discipline in AI. They have this field called AI for science. This has emerged in the 20s with these weather forecasting models with AlphaFold and so on. And it means that you are not just trying to brute force training a model as you can do for videos or with the pictures, where you can, just go through the internet, collect data and train and train and train. That will never be the case with physics data. And so you need to enforce physical constraints. In the architecture, you can enforce the constraints through the loss function, and so on, and to the training strategies. And so that's where we can maybe have a dialogue between industry and academia.
Okay, so I will stop asking you now the technical question because the time is running out, but I will also allow the audience to ask some questions, just a short one. Because I started that the turbulence is one of the unsolved problems, and this is like, it can become a source of motivation, or it frightens you and go away. So how did you end up in the field?
Well, no, you accept that your turbulence is just unsolvable. So probably in my lifetime it will be unsolvable. And but you look at the effects of turbulence, and actually turbulence. You understand a little bit more every day, and you understand how it is affecting a bigger problem like weather, like behavior in the arts. So turbulence is just one ingredient of the other, and you accept you cannot solve it, but you can simulate it, and you can understand little by little another aspect of turbulence, and that's very, you are never bored because you always find something new about turbulence.
And if I just may add, the movies are looking spectacular when you see all this turbulent behavior. So, so the question from the audience, please.
First of all, thank you for the nice talk. Coming to designing with these high-fidelity turbulent simulations, now what if we consider like different operating points, and you're talking about a design which should operate at, let's say, 2 different or 3 different Reynolds number, and then does the design with these high-fidelity still work at these other design points? And in that case, does like low-fidelity simulation still have a case for them?
Yeah, very good question. Actually, this is what we are accounting for that. We have, the project we have with Peter, we are trying to design a new compressor blades. And of course, we want the compressor blade to work well through different operational points. So the problem is even more costly because actually when you predict one point, you have to run several simulations because you have to span the range of conditions of interest. So we are running, in this case, 3 simulations, the design point and 2 extreme conditions. But you can also imagine to have a sort of surrogate, AI surrogate, which learns how the behavior of the system varies across conditions. Of course, in that case, you have to train the model for that, and you need more data. But yeah, we are definitely trying to design the model so that the behavior is robust across a range of conditions. It's not acceptable to have just the design point. It would be too risky.
Yeah. Thanks a lot for this very inspiring talk. I'm fascinated by turbulence as well, and plasma in my case, and chaos. So what's the point of predicting chaos? Because chaos is unpredictable in practice. Even round-off errors will produce totally different solutions, even with the best of your models. So what's the point, or how do you even think of training a data-driven something if even the basic data is not reproducible? You cannot reproduce chaotic simulation. So what's your take on this? Do you try to match
the statistics? You try to match the statistics, yeah.
But in practice, how do you do that? You have to assume that the statistics will somehow converge, right?
That's right. Actually, if you don't have any stationarity situation or homogeneity or something, it's really very, very difficult, because in that case you need to take ensemble averages, okay? But so ensemble averages are of course extremely expensive, because you have to repeat many times your experiment, which means repeat many times an HPC simulation by perturbing a little bit the boundary conditions and initial conditions. Otherwise, if you use the same machine, you always get the same results. But yeah, that's not doable. But in many cases, well, we are assuming that the system is statistically steady, so we are trying to match the time statistics, right? And there are many strategies for doing that. And one of the strategies could be either you just run your HPC simulation, you take the statistics, and then you train the low fidelity model to match the statistics of the high fidelity simulation. That's one of the things we are doing. Another possibility is to train the model to go to the same attractor. So you have an emulator of your turbulent system, and you, in the loss function, you try to get something which does not follow exactly the same trajectory, but moves to the same attractor. And people are trying to do that.
Thank you very much.
Perhaps I will just make the last comment. So, because this was about sustainability,
yeah.
So turbulence are encountered anywhere. So also in fusion. So basically, and maybe there you use AI from completely other stuff. So you control the whole thing. You make the ITER running. Then you will have enough energy to basically run your DNS simulation and optimize the blade. But maybe then you will not even need that, because this is the revolution. You would have a completely other machine.
But you know that turbulence is one of the big obstacles to nuclear fusion, because when you generate your plasma in a tomahawk, you need to perfectly control the shape of your plasma, and the small perturbations are perturbing the interface of your plasma, so it becomes asymmetric and stable. And so, yeah, I have talked a little bit with people at CEA, the nuclear energy entity in France, and they are working on understanding and emulating turbulence to control plasma, nuclear fusion. So that's, turbulence is everywhere.
Okay, thank you, Paola, for this really nice interview. So Peter is already anxious, so we should maybe leave.
Yes, no, well, thank Paola and Matej, thank you very much. So we will proceed. I'd now like to invite Sally Ellingson, who's the Papers Programme Chair, up to the stage, who's going to introduce the PASC 25 Best Paper presentation. So thanks, Sally, if you come up.
Thank you very much, Peter. So Kate Arneson is a research user interface and experience designer at the National Center for Supercomputing Applications at the University of Illinois Urbana-Champaign. She previously worked at the Pacific Northwest National Laboratory and Mayo Clinic. Through close collaborations with partners across academia and industry, NCSA supports projects ranging from chemistry and healthcare to social impact and data visualization. Combining a background in mathematics and art, Kate's work focuses on applying human-centered design and research to the creation of software products. In this talk, Kate will be sharing insights on the role and impact of user-centered design and research software development through case studies from Alpha Synthesis, an open-source software suite for chemistry research. In this work, Kate collaborates closely with scientists, engineers, and end users to create usable, reproducible, and sustainable applications, advancing the role of design in interdisciplinary research.
I don't know. Okay. Thank you, Sally, for the introduction. Before I begin, I want to thank the PASC 25 conference organizers and Papers Program Committee for the opportunity to share this work here and be here with all of you. I'd also like to recognize my co-authors Li Fu and Lisa Gatsky, who aren't able to be here to present in person today, but they've been incredible collaborators and contributors to the research and design work behind these efforts. So I want you to imagine a piece of software that you use every day. Maybe it's something for work, like for data analysis or a visualization tool, or maybe it's something in your personal life, like your calendar or notes app. Now think about what makes this application easy or difficult to use. Is it clear how to navigate the tool? Are there features that would be helpful for you but are missing from it? Did you need any support or instruction, just how to learn how to use the tool? Now try and imagine that same tool, but created by someone who knows very little about users like you, your needs, and your goals. Too often, that's the reality of scientific research software today. Tools are built by innovative researchers and engineers, but traditional development models often focus on integrating advanced technical capabilities while overlooking the actual needs of users. Mismatches between tool design and user workflow can result in complex interfaces, difficult features to use, and steep learning curves. At the National Center for Supercomputing Applications and the Molecule Maker Lab Institute, we're addressing these challenges through user-centered design, applying methodologies like user discovery sessions, iterative design, and usability testing to bridge the gap between researchers and domain scientists. Through this, we make scientific software not only functional, but more usable, reproducible, and sustainable. Today, I'll share how we approach this work and what it looks like in practice. We'll start out with a background on user-centered design and provide context for this work and how our team of designers operates within the research environment. Next, we'll dive into how this approach impacts the usability, reproducibility, and sustainability of the scientific software that we design. And finally, we'll reflect on some of the limitations of this work and where we see it headed next. So what is user-centered design, or UCD? As a broad term, it encompasses a number of related ideas. One major component is user experience, or UX. UX is commonly understood to encompass all aspects of an end user's interaction with a company, its products, and its services. Ideally, a good UX should be meaningful and relevant and provide a positive emotional impact. In the context of user interface or UI design, which incorporates visual elements such as layout, hierarchy, and interactive components, this translates into creating designs that are usable, accessible, intuitive, and efficient. A useful analogy is posed by web developer Dane Miller, who said, UI is the saddle, the stirrups, and the reins. UX is the feeling you get being able to ride the horse. So without the proper equipment and setup, riding a horse can be a painful experience. Similarly, good UI design creates and supports good UX. In the context of our own work, UCD refers to the process of creating research software that meets user needs and facilitates a positive UX. But what does it really mean to put UCD into practice? There are several well-established models on which we base our own work. One foundational framework is called design thinking, and while we won't dive into each step in this process, overall it emphasizes understanding user needs and iteratively exploring solutions through research, prototyping, and testing. Another common framework is the double diamond process, which relies on user input and iteration for exploring both the problem and solution space before determining a direction that will best serve end user needs. So while multiple representations of the UCD process exist, they all underscore the importance of deeply understanding users and the problems that they face, iteratively exploring solutions to meet specific user needs, and engaging users throughout this entire process. Although such practices are commonly integrated in commercial and consumer product life cycles, the same cannot be said of research software. This results in tools with significant challenges in providing either immediate or long-term user value, or both. Our solution to this, the inclusion of UCD in scientific software. To ground this idea, I want to share a bit of context for our own team's work, some of the types of projects that we work on, initiatives that we support, and the role of UCD in our day-to-day work. At the center of this work is Alpha Synthesis, an open source software suite developed within the Molecule Maker Lab Institute, or MMLI, which is a multi-institutional initiative advancing and democratizing chemical discovery through artificial intelligence and machine learning. Alpha Synthesis supports this mission by streamlining workflows for synthesis planning, catalyst discovery, process optimization, and closed-loop experimentation. Our design team is embedded within the Alpha Synthesis effort, where we collaborate closely with AI and ML researchers, aligning software solutions with chemistry domain user needs and goals. By applying structured UCD methodologies, we enhance the usability and impact of these tools in real-world research settings. To date, we've designed 7 publicly available tools within the Alpha Synthesis suite, with 3 more currently in progress. Beyond Alpha Synthesis, our design team is part of the National Center for Supercomputing Applications, which is a leading hub for computational research and interdisciplinary collaboration. Since 2020, our team has grown from a single designer into a dedicated user interface and experience, or UIX group, within NCSA. Since its official formation in 2021, the UIX team has contributed to more than 30 software products. We work on applications that span a wide range of domains, from molecular chemistry to genomics, to climate modeling and data visualization. For example, the African Kinship Reunion is a population genetics platform that facilitates familial connections of people of African descent around the world. InCore Studio is a platform that enables the modeling and analysis of community resilience to various hazards. Infodama, the forensic anthropology database for assessing methods accuracy, is a case management and methods analysis system for academic-based forensic researchers and anthropologists. So while each project is unique, they all require translating complex technical capabilities and features, as well as data, into tools that will integrate with real-world research workflows. To support this, we follow a structured UCD process that's grounded in frameworks like the double diamond process and design thinking that we looked at earlier, as well as shaped by our own experiences at NCSA. Our process includes 3 core phases. The first of which is discovery, where we conduct domain research and engage users to understand goals and workflows. The second is ideation, and in this phase, we iteratively develop designs, task flows, and prototypes that are informed by usability testing. And in the third phase, implementation, we collaborate closely with developers to create a complete software solution. This approach allows us to deeply understand user needs and iteratively refine our solutions. Let's take a look at how this plays out in practice through a few case studies from alpha synthesis. We'll start out with usability, one of the most visible impact areas of UCD. First, what is usability? It centers on how easily and effectively users can perform tasks, emphasizing intuitive interfaces, straightforward features, and minimal learning curves. Jacob Nielsen, a pioneer in the field of UX, defines it using 5 principles, which are learnability, efficiency, memorability, error recovery, and satisfaction. But scientific software can be a bit at odds with some of these principles, particularly due to the inherent complexity of its subject matter and applications. Tools can be powerful, but if they're difficult to use, they're unlikely to be adopted. Let's take a look at how we use UCD to tackle some of these challenges within alpha synthesis. SOM is a predictive tool designed to accelerate workflows for CN coupling reactions, which are commonly used in pharmaceutical research and manufacturing. This tool allows users to efficiently predict useful conditions for their specific reactions, allowing them to bypass the extensive lab work that's traditionally been required to do so. When our team joined this project, the original technology already existed in the form of a command line tool. Our research collaborators who built this functionality, their initial goal was to replicate the existing workflow, but in a more accessible graphical interface. However, early design research and user interviews revealed diverse needs amongst our user base and prompted a more intentional and nuanced design approach. So we set out to create a minimum viable product, or MVP. In product development, an MVP is a functional version of a tool that focuses on supporting essential features and core workflows, but perhaps not all possible workflows. This enables us to produce effective solutions more quickly, gather user feedback, and then iterate on future states accordingly. For SOM, defining an MVP meant identifying the most immediate, high-impact user needs. We first focused on supporting experimental chemists who wanted to explore a single or a small set of reactant pairs. This allowed us to explore the most essential features, like how to input reactant pairs and explore predicted conditions, while laying the groundwork for future versions that would support more complex use cases, such as batch analysis for computational chemists. Enhancing SOM's usability beyond that of the original command line tool, our designs incorporate the display of molecule structures, in addition to the original smile string format, reducing cognitive load and enhancing familiarity for experimental users. An interactive yield percentage density plot allows users to rapidly assess the viability of various conditions and focus in on those of interest. And finally, we implemented onboarding resources such as tutorials, contextual examples, and access to training data to enhance learnability. Through an iterative user-centered approach, SOM evolved from a powerful command line tool into a software solution that's more usable, accessible, and impactful. Another example is Novastoic 2.0, a tool designed to support metabolic researchers and engineers in exploring biosynthesis pathways. Unlike other tools in this space, which often lack integration or support for database missing molecules, Novastoic combines 4 advanced technologies in a single platform, enabling more efficient pathway design and novel route discovery. As with SOM, the technical methodology for this tool already existed when we joined the project. This time, however, the research team had also created an early interface version of this tool. We're able to use this prototype as a starting point to identify key features and technical constraints, as well as to guide user interviews and usability sessions with domain experts. This approach surfaced common workflows, behaviors, and pain points, and directly informed our design solution. One key observation was that users had varying level of expertise and familiarity with using molecular representation systems. Less experienced users struggled to understand the KEGG ID formats that were utilized in the original prototype. So we set out to explore the design challenge. How might we present unfamiliar data in a way that a wider audience could easily understand while maintaining a seamless flow within the tool? We took an iterative approach to explore this question, generating and evaluating numerous design ideas. For example, we explored supporting alternative input formats, such as common name, smiles, metanetics, and structures. We also tested explicitly pairing molecular images with the inputs to improve recognition and reduce ambiguity, which is a similar concept to some of our work in SOM. And we also worked to increase hierarchy and reduce visual clutter for complex tabular data. As a result, the implemented Novostoic tool supports multiple input formats for increased recognition and clarity, especially for more novice users. Further reducing cognitive load, expandable rows and hover interactions allow users to progressively access more detailed information while minimizing redundancy and visual complexity. And overall, the results page streamlines the process of assessing viable pathways, emphasizing key data like theoretical yield and Gibbs energy through visual hierarchy with larger, bolded fonts. Through these user-centered solutions, Novostoic has transformed into a more intuitive, efficient tool for biosynthesis pathway exploration. So in the case of both SOM and Novostoic, UCD helped us to identify mismatches between what research teams assumed users would need and what users actually needed. By involving users throughout the design process and continuously iterating on solutions, we're able to create tools that are easier to use and more effective in practice. Beyond this, our design process also helps to enhance reproducibility, which we'll take a look at next. Reproducibility is widely recognized as crucial to scientific progress, yet the identification of a reproducibility crisis across various domains highlights significant ongoing challenges. Through UCD, scientific software can play a critical role in addressing these issues. In the context of software design and development, reproducibility can be understood in several ways. The first is in terms of the software itself, and the ability to create consistent code and user experiences across time and platforms. The second is in terms of user workflows. How can we facilitate familiarity and recognition between related tools and workflows? And the third ties back into scientific reproducibility, such as incorporating features that will support and enable repeatable processes and experimentation. One of the key ways that we enhance reproducibility at the software level is through the use of standardized design systems and component libraries. These systems integrate pre-built components with styling guidelines and corresponding code and create a shared language between designers and developers. They make our internal processes more efficient, and they also support end users. For alpha synthesis, we leverage the PrimeNG design system, and you can see here the consistent use of components and interactions across tools like the tab navigation, request options, and export buttons. This uniformity creates a consistent look and feel across the alpha synthesis suite and familiar interaction patterns that reduce cognitive load for our users. Given the highly technical nature of the scientific software we produce, however, most of our projects also require custom components or data visualizations. So as tools are added to the alpha synthesis suite, we gradually augment our component library to include more robust, domain-specific components and interactions. For example, we designed molecule cards, which are a standardized format for displaying chemical information, which can be adapted between tools and molecule roles to best suit the information needs of each use case. This further enhances familiarity and enables ease of use across projects. Building up design components and interactions into larger software products, we also enhance reproducibility at the workflow level. Across alpha synthesis, we identify similar workflows from real-world research and then translate them into workflow alignment between the tools themselves. For instance, ACE Retro and RTS-CESP are both tools for chemoenzymatic retrosynthesis planning. While they each leverage unique models and methodologies behind the scenes, they share significant overlap in workflow. The pathway visualizations pictured here reflect this alignment. Each contain analogous information like molecule cards and color coding that enables users to evaluate recommended synthesis routes, molecules, and reactions. Finally, at the science level, we embed features to enable repeatable, transparent workflows. To name a few, these options include the ability to access previous job results, export structured job results, adjust parameters, and rerun experiments. Consistent navigation and progress indicators help users to know where they're at in each step of the process, and clear views that track inputs, outputs, and settings help to minimize errors and facilitate repeatable experimentation. So while reproducibility is often seen as a scientific challenge, it's also a design opportunity, and one where user-centered approaches can make a significant impact. The same is true for sustainability, which we'll dive into next. Like reproducibility, sustainability can be understood in a few different ways. In scientific software, this extends to beyond the initial implementation into how well a tool can adapt to evolving user needs and bases, integrate within larger ecosystems, and drive equitable access to research innovation. But research software is often developed using an isolated approach and limited foresight, which can result in barriers to sustainability over time. In the case of alpha synthesis, however, UCD helps to ensure that tools are scalable, responsive, and cohesive, all within the broader mission of supporting global goals for development. All alpha synthesis tools begin with an MVP, a focused initial release that prioritizes key features and essential user workflows. But the product lifecycle is much more than that, and through UCD, we create product roadmaps that guide long-term planning and help to ensure that tools remain relevant and adaptable over time. A good example of this is Reaction Miner, a chemistry tool in the literature mining space that allows people to search for chemical reactions, molecules, and text. When we first joined the project, early user research and interviews revealed critical pain points in the existing technology. So we documented some of the key requirements and workflows and brought these findings back to the research team for iteration. Over several months of collaboration, this has led to the integration of critical features, such as multi-document analysis, and the integration of structural visualizations, shaping a tool that's designed for lasting impact. Beyond individual tools, we're working toward a more cohesive suite of MMLI resources that will serve the broader chemistry research community. Already, NovaStoic integrates 4 advanced technologies for biosynthesis planning in a single platform. An open enzyme database combines community-driven data sharing with multiple models for prediction and recommendation. By using consistent components, workflows, and a visual language, we support not only the scalability of individual tools, but also the future integration between tools, laying the groundwork for a more unified and interoperable ecosystem. Finally, our work on alpha synthesis also supports sustainability in the context of global development goals. By designing open source tools, we're helping to engage diverse contributors through community-driven efforts like Open Enzyme Database. User-friendly, web-based tools expand access to cutting-edge models and technologies that serve not only experienced professional researchers, but also early career scientists and students alike. This approach advances the sustainability of software within the science space and highlights MMLI's role in driving equitable innovation in the research community. Well, UCD has already advanced the usability, reproducibility, and sustainability of the software within alpha synthesis. We'd also like to share some of our next steps for how we're working to address the current limitations of this work. First, our user research has primarily been concentrated within the user group of MMLI. This has led to close collaboration, but a key next step is incorporating input from a more diverse range of participants and enhancing generalizability. Second, as alpha synthesis continues to grow, improving data flow and interoperability between tools will be essential to support seamless integration and long-term integration within the larger ecosystem. And finally, we're working to expand our analytics beyond basic metrics to better understand user behavior and enable more responsive and dynamic iteration over time. Throughout this talk, I've shared how user-centered design can make scientific software more usable, reproducible, and sustainable. By incorporating practices like user discovery sessions, iterative design, and scalable, consistent systems in the software development process, we're bridging the gap between technical solutions and end users, ensuring that innovation is not only functional, but valuable. This approach has transformed how we work at NCSA and MMLI, and we believe it has the potential to impact scientific software in the broader research community as well. I'd like to thank MMLI and the National Science Foundation for their support of this work, and again to the PASC 25 organizers for the opportunity to share it. And to all of you, thank you for being here. I'd love to connect, answer any questions, and hear about how you think about UCD in your own research environments. Thank you.
Thank you, Kate, for the great talk, and congratulations again on your Best Paper Award. And I would like to ask the audience if they have any questions for Kate.
Thanks for your talk. So I saw in one of my voice sounds very weird to me. I'm wondering. So in one of your slides, you show like a team of five people and 30 software. So my question is, how do you scale? How do you keep developing these things, or are you giving them back to the community? How does it work?
Yeah, so it depends a little bit on the project, I guess, and the funding source. So sometimes our projects might be scoped for, at the shortest, 3 months. Some of them end up being a year. Some of them, now we're on a grant that's 5 years with the opportunity to renew for another 5 years. So it really depends on the funding source, I guess, as well as the availability of the different designers on the team. So in the most ideal case, we'd be able to touch a project for longer so that we can keep iterating over time. But sometimes it does involve definitely handing off to external collaborators as well and trying to figure out a plan that will make it maintainable for them.
Thanks. Yeah, but I think so. You're talking about 5 years, which I think makes sense. But sometimes in the academic world, we're talking about a year or 2 years of funding. So that's kind of a challenge, I guess. But thanks. Yeah, pretty cool.
We have another one in the back.
Yeah, thanks for the presentation. You mentioned the sustainability, and but I only quickly mentioned the sustainability for developers about the open source, give back to the open source and give back to the community. And my question is, yeah, you already mentioned the scale of your team, and then how, for example, how many people you need for like one specific tools you mentioned, and how much time required to onboard a new developer, and how much like outsiders, contributors that you have for any tools you just mentioned that you have for like can really give like you get in the contribution from you mentioned make it open source.
Yeah. So again, a little bit project specific. Some of the tools that we've worked on here within Alpha Synthesis have like one main researcher who's working within like a research lab. In the case of MMLI, it's usually UIUC, also Penn State and RIT. So sometimes it's one main researcher that we collaborate. Sometimes it's an entire research lab that could have maybe 10 people in it, often led by a professor as well as contributing PhD students as well. So that depends a little bit. As far as our team goes, we usually have one primary designer supporting each of the projects. So one of my co-author, Lee, who's not able to be here, we work a little bit together because these tools end up being related. So we'll each lead one of the projects, but then we meet regularly to make sure that the components we're using between the tools are similar and consistent. We also have, at NCSA, we have a lot of developers that we collaborate closely with as well. So we have front-end developers, back-end developers, and as well as a role called research scientists. So they're kind of like our embedded in-house domain experts. So for each one of these projects, you'll have a handful of developers, a research scientist, a designer, and then the research team that ends up creating the kind of technical capability.
Another question over here. Peter.
Hi, great talk, really like that. My question is, do you think some of the key sort of pillars of our ecosystem, which are the funders, institutions and journals, are doing enough to support your sort of thesis, as it were, that this needs to be done? And if they're not, what more could they perhaps do?
I'd like to think that it's headed in that direction. As I kind of mentioned, 5 years ago, even at NCSA, we had one of the other co-authors on the paper. She was the founding designer at NCSA, and so she's done a lot of work within our own kind of research environment to advocate for the inclusion of UX in these projects. It's something that, because we'll be dedicated to a particular project, it's something that does need to get written into like any grant proposals or applications. So I think having at NCSA as well, we have a lot of people in leadership roles who recognize the value of it, and so it does need to kind of be a systemic effort, I guess, and a lot of people end up needing to get involved to make sure that it is included in the funding sources. It's something that there's a group in the US, it's the US Research Software Engineer Association. It's something that we're seeing growing more as well, the inclusion of UX, but there are often times where there just isn't like the bandwidth or I guess the recognition that this can be a dedicated role. So yeah, I hope I see it heading in that direction, but I do acknowledge that definitely in the past at NCSA and likely in other places as well, it might not be written into funding to support something like this.
Thank you.
I do believe that we are at time now. I did see some other hands, so I invite Kate to stay around during the break and come talk to her if you have more questions, and find out if there is any online as well. But thank you, and please join me again in congratulating Kate on her great paper and award.
Right, thanks, Kate and Sally. It's fantastic. I'm now going to invite Dave Moxey up onto the stage, who is part of the poster program and is going to introduce the second round of Flash poster talks, all lined up over here. So over to you, Dave.
Thank you very much, Peter. So yes, hello everybody, and thank you very much for coming. I am here to introduce our next range of wonderful poster presenters. This is following on from the presentation sessions we had yesterday as well, and we already had such a great range, and we have even more today. So my first job really is to remind all of you of the poster session. So if you weren't here for yesterday's session, we have a poster session this evening at 7 o'clock, and this is held jointly with the reception. During that time, you're going to get the ability to vote for who you believe has the best posters. So there's these little cards which you should complete. As we go through the presentations today, each of the posters will have a little code on it, and you can pop up to 2 of those on your card, and then indicate, pop those back in the blue boxes to cast your vote. So I really encourage everybody to have a really good look around the posters today and get those through. And we'll announce the Best Poster Award in the closing session on Wednesday. So this session is all about giving each of our poster presenters a quick 30-second pitch. They come from a really wide range of fantastic institutions across a very broad range of backgrounds. So I'm not going to introduce everybody's affiliation here, but their job is to spend about 30 seconds, up to 30 seconds, pitching their presentation or their poster to you and hopefully convincing you guys to come and see them in the poster session later today. So, without further ado, I will invite each onto stage. Just as a reminder, there's a little clock in the bottom corner of the slides. When you get up here, you'll have a reference for how long you have left. So, our first presentation is from Mauro Bianco, who will talk about integrating the icon for Pi Python-based dynamical core into icon.
Yeah, tomato. I'm not Mauro Bianco, but this is our poster. We implemented the icon die-core in GT4Pi. It is a lot more readable than Fortran, and it is also competitive in terms of performance. We implemented some cool GT4Pi features, and we also did some refactorings, so now we can split between predictor and corrector steps. We also did some renamings, so now stencil name reflect what stencils actually do. And we also have a lot of cool backends that the code is compatible with. So the code is also open source, and ladies and gentlemen, P27. Thank you very much.
Thank you. So our next presenter is Felipe Nana, who will talk about interactive visualization of high-energy physics events via NVIDIA Omniverse.
Simulations play a central role in high-energy physics, both for detector design and event reconstruction. Yet, for a long time, visualization of simulated events has been limited by processing constraints. So in my poster, I am presenting a workflow using NVIDIA Omniverse platform to allow real-time visualization of particle interactions, and with a basic geometry detector, I will try to demonstrate the performance of such approach. So if you are interested, stop by poster 28. Thank you.
Thank you. So our next presenter is Matteo Benino, Maria Girone, and Andreas Linterman, who will talk about InTwin AI, I don't know how to pronounce that, sorry. Enabling scalable AI workflows on HPC for digital twins in science.
All right, so we just heard a wonderful talk about UX, and that's kind of what we're trying to achieve as well, so to help scientists to access HPC resources for the AI workflows on HPC. So in this European project called InnerTwin, we have been developing this tool called iTwin AI, and the goal is to help scaling distributed training and hyperparameter optimization on HPC, supporting a wide variety of scientific use cases, including both use cases coming from physics and climate research. Not only we're interested in scalability, but also in profiling the energy consumption and understanding the impact of that. So if you're interested, come to poster 29. Thanks.
Thank you. So our next presenter is Matthew Lane, who will talk about the mentor interpretation agent from network embeddings to mechanicalistic narratives via retrieval augmented LLMs.
Thank you. So gene set interpretation can be rather hard and time consuming. So we have built a software product that is a LLM agentic pipeline that can break these really difficult processes apart into small bite-sized chunks for these LLM agents to actually, very easily interpret. And then finally, what it does is then output these into nice, readable documents for the users to then use to help guide their human-in-the-loop interpretation. So please, if you do have any interest in LLMs, come see me at poster 30.
Thank you. Our next presenter is Shivam Sundriel, who will talk about mixed precision customized for discontinuous Galerkin methods.
Hello all. The discontinuous Galerkin method has a lot of advantages, but at a major memory cost. In this work, to overcome this issue, we come up with a new data structure inspired by the block floating point format, drastically reducing the memory footprint. We use a shared exponent as well as an adaptive encoding strategy for higher polynomial degrees. In the simple case of the 1D linear transport problem, we are able to save 33% of the memory while having comparable accuracy to the single precision float. If this is how much memory we can save for this simple case, how much can we save for higher dimension and higher polynomial degrees? To find that out, come to poster 31.
Thank you. So next we have Matthew, Matthew Lane again.
I'm back.
He's back. He will talk about a second poster, multi-omic single network perturbation for phenotypic prediction.
So phenotypic prediction can be rather difficult as well. So we've built a model such that we can actually knock out genes and model these knockouts so that researchers don't have to do the costly or arguably immoral actions of doing those knockouts in, say, animals or what have you. So from there, we can take that output, that knockout output, and then model which genes in that topological network are most affected by these knockouts, and then see potential for drug repurposing and so on and so forth. So please, if you're interested in networks, come see me at Poster 32.
Thank you. So next we have Johan Eriksson, who will talk about optimizing data offload in the IFS using GPU-aware data structures and source-to-source translation.
Yeah. So hi, at ECMWF we do numerical weather prediction, and the IFS is our operational numerical weather prediction model. And when making this run on GPUs, we have a Fortran library called Field API that has GPU-aware data structures, and we're using a source-to-source translation tool that can generate CPU Fortran code to GPU Fortran code. And in this poster, we show how this can automate the process of doing blocking of loops to make asynchronous offloads and overlap data transfers and communications. And if you're interested about this Fortran compiler technology, come talk to me. Look at poster 33. Yeah.
So I believe our next presenter will be Samuel James Newcomb, who will talk about performance, portability across different mathematical models, hardware, and simulation scenarios in molecular dynamics.
Hi, so I'm Sam, and I'm working on this very exciting topic of algorithm selection in particle simulations. So firstly, I'm going to be talking about what are these algorithms I'm selecting from, and discussing how they're different for different mathematical models for the interactions between the particles or different hardware, and how we can select the best. Okay, and so I've got discussion on the algorithms, discussion on the selection process, and also looking in particular at rigid body models and how we can achieve this optimal performance across all of these algorithms we're using for this particular kind of model.
Thank you very much. So our next presenter is Emily Bourne, who will talk about PySol, automating translation of Python prototypes to C and Fortran production codes.
Hi. Everybody likes coding in Python, right? But in HPC, usually what we actually need is Fortran or C code. If you've ever found yourself translating from Python, please come and see our poster. Pixel automates this for you, and it provides a Python interface, which means you can keep using your Python testing suite and calling all of your code from Python in the same way that you did when it was just Python code. Please come and see our poster. We're at the bottom of the stairs. We have translated code, examples of the workflow, and comparison with other Python accelerators.
Thank you very much. So our next presenter is Keshvi Tuteja, who talk about PyGinkgo, Python bindings for Ginkgo.
Hello everyone, I'm Keshvi and we are working towards developing Python bindings for Ginkgo or PyGinkgo. Ginkgo is a sparse linear algebra library with a special focus on sparse linear systems. So we make Ginkgo's high-performance kernels accessible from within Python. If you are interested about the performance results or if you want to contribute to PyGinkgo, drop by my poster P37. Thank you.
Thank you. So our next presenter is Rito Kuromanaka, who will talk about scalable genomic context analysis with GC-SNAP2 on HPC clusters.
Thank you. Hello, everyone. Have you ever wondered how biologists identify the function of proteins? Well, one approach is to use genomic context analysis, where they analyze the neighborhood of the genes and create such lovely plots as you see on this poster. There are tools like GC-SNAP1 Desktop. However, these tools have some limitations, especially regarding execution time, therefore are not made to do large-scale analysis. So if you are interested how we port a GC Snap to a HPC cluster, please visit me at Poster 38 this evening, located right outside the doors of this room. Thank you.
Thank you. Our next presenter is Thomas Meyer, who will talk about simulations of giant impacts with material strength in PKD Grav3.
Thank you. So we simulate collisions between planets to explain their peculiar characteristics. And at past PASCs, I showed how we moved from doing that at a few 100,000 particles to a few 100 million particles by introducing PKD Grav3. And this time, I showed that because at smaller bodies, we need material strength, while at bigger bodies, we can model the bodies as fluid. Now, we can do that in PKD Grav3 too, and I show simulations with up to 2 billion particles of a cratering impact on Mercury. If you're interested in any of that, please visit me at Poster 39. Thank you.
Thank you. Our next presenter is Jacopo Palombo to present their poster on spectral methods for the clustering of cyclic and acyclic graphs.
Hello, everyone. So we explored different methods for the clustering of directed cyclic and acyclic graphs. Acyclic graphs in particular are very common in real-world scenarios, such as trophic networks, interbank depth exchange, and email exchange networks. We did experiments on both synthetic graph based on a directed stochastic block model and on a real-world dataset of email exchanges across different European research institutions. So if you're interested in the clustering for directed graphs, come to P40. Thank you.
Thank you. Our next presenter is Jonathan Schmalfus, who will talk about sickle and block structure grids, performance impact on simulations of complex coastal ocean domains.
Taking a look at the unstructured, typically used grids for ocean simulations, we explore block-structured grids, a collection of structured blocks, and show performance results for varying algorithmic strategies, all employed utilizing sickle for shallow water equations code. And we showcase for GPUs, CPUs, our problems and our already nice speed-ups, but we want to, of course, increase them. So we're looking for help and opinions on what we're doing wrong. Thank you.
Thank you. Our next speaker is Sonali Mayani, who will talk about towards exascale particle mesh methods, a massively parallel performance portable C++ particle cell framework.
So I'm not Sonali, but I'll present this anyway. So the landscape of HPC architectures is constantly growing, so one needs to think about making simulation code portable. We present IPPL, a open source C++ framework that provides users with a modular framework for performance portable particle mesh simulations that uses Cocos as a hardware abstraction layer. The framework has many building blocks, such as particles, interpolation schemes, grids, and PDE solvers. The example showcase includes applications to cosmology and plasma physics. So if you want to know more about this and make your code performance portable, please come by our poster.
Thank you. Our next speaker is Murph Fadai, who will talk about designing biomimetic materials for carbon capture, leveraging high-performance computing for large-scale molecular dynamic simulations to advance sustainable solutions.
Yes, that's basically what I mostly wanted to say anyway, but it's all in the title, right? So in our group, we are doing basically soft materials and modeling them for these like sustainable applications. Specifically, I'm looking into enzymes and interfaces and their interactions with these interfaces, and I model graphene surfaces and graphene oxide surfaces that is highly oxidized. So I show the workflow of basically optimizing this from our previous code that would run for like a month to now it runs only in an hour. And if you want to see the results of these unique surfaces and in their interactions and their morphologies and all that, come see me in ACM P01. It's hidden in foyer. If you can find me, I'll be glad. Thanks.
Thank you. Our next speaker is Patricia Harato Moreira, who will talk about development of a predictive model for the prognosis of patients with breast cancer.
Hello, everyone. My name is Patricia, and I'm from Brazil. I'm here to present the development of a predictive model for the prognosis of patients with breast cancer. In this model, I use the only complete blood count test results from 8,000 patients from the largest hospital of cancer in Latin America, ICESP. If you want to see more about how I developed this project and how can AI be used to predict the recurrence of cancer in patients, you can see my poster in ACM P002. Thank you.
Thank you. Our next speaker is Vincent Maillot, who will talk about distributed computing for spatiotemporal Bayesian model using the Inland method.
Hi, everyone. So today I'm presenting to you a novel framework to perform large-scale Bayesian inference using the Inland methodology. So we aim at bridging the gap between current state-of-the-art framework and high-performance computing. In detail, we are presenting several parallelization strategies, and we focus on linear solver tailored to accelerate spatiotemporal Gaussian process modeling. So if you're interested to understand how we scale to hundreds of GPUs, a method that so far was limited to shared memory CPU architecture, please drop by. Thank you.
Thank you. Next, we have Sonali Mayani, who will talk about a performance-portable, matrix-free finite element framework for particle mesh methods.
Now it's really me. As we all know, we want to run on heterogeneous exascale supercomputers, and in order to do that, we need performance portability. So we're presenting a matrix-free finite element framework in the context of the IPPL code that was presented in poster 43, which is based on COCOS, which is how we get our performance portability. And this is matrix-free, so we avoid all the memory costs incurred by building a full finite element matrix, which is especially important on GPUs. If you would like to know more about our finite element framework, please come find me at ACM P05. Thank you.
Thank you. And finally, I believe to conclude our session, we have Nicholas Casarino, who will present Understanding HMM Performance for Enhanced HPC Portability.
Yes, hi. HMM is a infrastructure by Linux that allows you to use heterogeneous computers without having to explicitly manage the memory between host and device. This is helpful for scientists that can write more simple and portable code that is not specific to one architecture, though HMM is currently 4 times slower than its proprietary counterpart. So my research goes into understanding and addressing that performance difference. Thank you.
Thank you. I believe we have one more presenter. I don't have the details, so I will let them introduce and present their posts themselves.
Sure, thank you. Hi, folks. My slide is not up, but I'm Hanna Ferluchkai from the University of Texas at Austin. We conducted an interview study of many teams across the Exascale Computing Project, which was a 7-year initiative to build scientific software. And if you're curious about software collaboration between researchers who know nothing about software engineers who know nothing about research, and people in between, come talk to me, P4, all the way in the back of the other room. Thank you.
Thank you. So it just leaves me to conclude. My apologies to Ryan. I think from P43 we had a bit of a mix-up with your name on the slide, so thank you for that. And also, just to say it's been an absolute privilege to be on the committee this year with so many fantastic posters. So make sure that you go ahead and vote for your 2 favorite posters. Look forward to seeing you all in this evening's session, and maybe just one round of applause for thanking all of our poster presenters. So with that, I think I'll hand back to Peter.
Thanks, Dave. So that concludes the morning's session. So thank you again to all of the participants and speakers. It's been fantastic. We can now go and have a break until, I think, 11:30. And at 11:30, all of the parallel sessions will start. If you're speaking in one of the parallel sessions, just remember to head over early to find the room that you're speaking in. So we're done.